Today we're going to take a look at integrals with exponentials and natural logs. Alright, so the first thing is, think about it when we integrate it. Say this is the derivative. Okay, what is it beforehand? Well, e to the x isn't too bad. This is going to be e to the x plus c. Okay, but we're going to add some u substitution in here, because here, if you look at number 1, it's not as simple. Okay, we just don't have x up here. So I need to make u 3x plus 1. Well, when I differentiate that, that makes 3 dx on that side. The problem is I don't see the 3 here. I do see the dx. So what I've got to do is divide by 3. So 1/3 du equals dx. So when I replace dx, I'm replacing it with 1/3 du. All right, and now I can say e to the u. Well, here when I integrate, it's going to be 1/3 e to the u plus c. Now we just need to replace u. It's going to be 1/3 e to the 3x plus 1 and then plus c. All right, moving right along. We're going to do the same thing here. Again, this is just not an x as the exponent. All right, so here we have to say u is negative x squared. All right, so here du equals negative 2x dx. Now, I have the x and I have the dx. The problem is I don't have the negative 2, and then I've got this extra 5. So here, I'm going to make it negative 1/2 du equals x dx. So this x and dx go away, and I'm going to replace it with negative 1/2. Now this 5 is going to stay here. I'm going to make it like this. I'm going to bring it out with the negative 1/2. And then make this e to the u. So now this is going to be negative 5/2 e to the u plus c. And now let's go replace the u with negative x squared. And again, if you want to take the derivative of this, see if you get this function right there. And we should. All right, moving right along. Let's go to number 3. Again, at any point you want to stop, you're welcome to. Now, I honestly would rewrite this. Okay, I would rewrite it so it's x to the negative 1, and then also this x squared in the denominator, x to the negative 2. All right, and the reason is because what if I take my u and say x to the negative 1? All right, and I differentiate that, so du equals negative x to the negative 2 dx. Look what I've got. I've got x to the negative 2, which is what I need. Okay, if I didn't have that, I couldn't do it this way. All right, I just don't have the negative, so I'm going to move the negative to the other side. Okay, and I'm going to replace this entire thing with negative du. So negative du, and then replace e to the x to the negative 1 with e to the u. So now when I integrate it, negative e to the u plus c, and now go replace u. And I'm going to go ahead and change this back to 1 over x. All right, same thing here. I start looking at this, and this is e to the cosine of x, but I got the sine x here, and oh, wait a minute. Okay, the derivative of cosine is negative sine x. Okay, so if I make u cosine x, and then I take the derivative, and notice the only thing I'm missing is that negative. So I can replace this sine x dx with negative du. All right, and then this e to the u. So this makes negative e to the u plus c, and then go and replace it. All right, moving right along. Again, if you want to do some of this on your own, please do. All right, now we see that we have the other ones that were indefinite integrals. Now we have definite integrals. Okay, so u equals negative x. Okay, what du equals negative dx. I'm just missing the negative on the other side. So this is going to be negative. All right, e to the u du. However, remember, we want to replace our bounds. So u to the 0, when I plug 0 in here, I get 0. U to the 1, when I plug 1 in there, I get -1. Now, it's okay, this is larger than that. All right, so here we go. This is going to be basically negative e to the u, and it's going from 0 to -1. All right, so negative e to the -1 minus negative e to the -0. Or 0, sorry, not negative. All right, so let's go clean this up a bit. So this e to the -1 really makes -1 over e. And that makes plus, and then anything to the 0 power is 1. Okay, you may actually see it written as 1 minus 1 over e, like that. All right, moving right along. Now, when I go and look at this one, okay, now, this is cosine of e to the x. So here, if I make u equal to e to the x, and then du equals, when I take the derivative of e to the x dx, I notice I have e to the x dx. All right, I'm good on that. I don't even need to move anything. All right, so here, it's just going to be the cosine of u du. Change my bounds. Okay, so what I've got to do is, I got to do u of -1. That's going to make e to the -1. And then u to the 0, u of 0, that's e to 0, well, that equals 1. Okay, so here we go. When I integrate this, this is going to be sine u from e to the -1 to 1. So this makes sine of 1 minus sine of, and I'm going to go ahead and make this 1 over e. And there we go. We can't do anything with that. Unlike logs, if we had a logs, we could combine it together using the log properties. All right, moving right along. Let's look at this right here. Now, so we dealt with e to the x. What about a to the x? Okay, if I'm trying to integrate a to the x, it is going to be 1 over ln of a to the x plus c. Now, we don't see this a lot, okay, but it will pop up. So make sure you have it memorized. Okay, so here we go. This is going to be 1 over ln of 2. All right, and this is just basic right here. And then times 2 to the x plus c. And a lot of times you may see 2 to the x over ln of 2 plus c, like that. All right, now, when I start looking at this one's a little more complicated. All right, so what if I make my u 3 minus, whoops. It's going to be 3 minus x and then squared. All right, so let's see, does that work? If I do this, I can say, all right, du equals 2 times 3 minus x, but don't forget the chain rule. People will always forget this. You got to multiply it by -1. All right, and then dx. So really, this is like we've got this -2 out here. And if you notice, I do have 3 minus x. I don't have the -2. So I'm going to have to do -1/2 du equals 3 minus x dx. So I do have this right here. All right, so I'm going to put the -1/2 on the outside. This is going to be 7 to the u. All right, so when I go to integrate this, all right, -1/2, all right, times, if you need to, go back and look at this up here, 1 over ln of 7 times 7 to the u, because we're using u in this case, plus c. Now we go to replace the u. I'm going to go ahead and put the 2 and the ln of 7 in the denominator together. You are also welcome, instead of putting this 1, it's going to be like 1 times 7 to the u, 7 to the, all right, 3 minus x squared up there. Okay, make sure you have enough room on your paper. I kind of ran out of room on my board. Okay, here we go. Number 9. When I start looking at this one, I see, oh, sine and cosine, those are derivatives of one another. So if I make u sine x, and I say du equals cosine x dx, guess what? I got the cosine x dx. All right, so this is just 2u du. So this is just 1 over ln of 2 times 2 to the u plus c. Now go replace u. So it's going to be 2 to sine x over ln of 2 plus c. All right, moving right along. Now, when I see this right here, recall that this is x to the negative 1. Okay, so when we had x to the negative 1, remember, when we integrate is ln absolute value of x plus c. All right, so here we go. Now again, if you want to change this so it looks like that right there, you're welcome to. All right, and so this is going to be 2 ln absolute value of x plus c. Now, please realize if it's a short answer, you can leave your answer like this, but remember your properties, okay? This can actually make natural log of x squared plus c. And I can lose the absolute value, and the reason is because anytime we square a number, it's positive. All right, so realize that these two things are the same thing. All right, number 11. Now, this is a little more complicated. Right here. You could say this is to the first power. And so what I can do is actually say 4x minus 1 to the negative 1. Well, here, what if I make u equal to that 4x minus 1? And the reason why I have to do that and do u substitution is because right here when I take the derivative, I really need that 4. And I don't have the 4. So this is 1/4 du equals dx. So here, this is going to be 1/4. All right, u to the negative 1 du. All right, so here this is going to be 1/4 ln the absolute value of u plus c. We'll go replace it and keep the absolute value. All right, now same thing on number 12. When I start looking at this, I see tan x and I see secant squared x. Well, the derivative of tan x is secant squared x. So I probably want my u to be tan x. But what I'm going to do first is I'm going to make this tan to the negative 1 of x. All right, and make my u tan x. Okay, and I do have the secant squared x, dx. I can replace that with du. All right, and my tan x, now that notice that's tan to the negative 1, so I'm going to change that so it's u to the negative 1. Well, remember, u to the negative 1 is just natural log, absolute value of u plus c. Now we can just replace the u in there, and it's like that. Okay, let's look at number 13. Now, this one's a little more complicated. You are welcome to do 2x and then x plus 1 to the negative 2. Now, I notice I got to the negative 2. What if I do u as x plus 1? du equals just dx. Okay, and I've got the dx. My problem is I've got this extra thing right here. Well, remember, when we have an extra x, we can put this in terms of u. So u minus 1 equals x. All right, so what I can do is I still have the 2. All right, change that x right there to be u minus 1. All right, and now this is going to be u to the negative 2. Well, remember what we can do? We can distribute. You can distribute the 2 in there as well, and I think I'm going to do that. So it's going to be 2u to the negative 1, all right, minus 2u to the negative 2. And you can split these 2 up if you want, or just work with it together. I'm just going to work with it together. U to the negative 1, that's going to make ln absolute value of u. All right, now this one, remember, we add 1 and we divide by whatever this exponent is. Okay, so I'm going to clean it up and substitute what u is. That's going to make a positive 2. All right, and then since this is u to the negative 1, it's going to go down low, so x plus 1 is in the denominator. All right, don't forget that you do need the absolute values. You will be taken off if you do not have them. So some tricks to this are you want to look for basic integration. Okay, so let's look right here. So some tricks are look for basic integration. Okay, rewrite function using your identities. Okay, long division and splitting up fractions. I'm going to show you something with long division in just a second. And then if you need to, use substitution. All right, so let's go back. Let's go look at number 14. I do have some extra. Now, for this one, you don't want to use substitution from the beginning. Do you see how both of these have the same degree? You may want to come out and do some long division here. X squared plus 1 goes into x squared plus x plus 1. Here, x squared goes into here once. When I go to multiply, I get x squared plus 1, but remember, we're subtracting, so I change my signs. These eliminate, and I'm just left with x. Okay, well, x squared doesn't go into x, so what I do is say plus x over x squared plus 1. Okay, so when I go to integrate, I can change that to 1 plus x over x squared plus 1 dx. All right, if I want to, I can do this. I can just distribute the dx throughout this entire thing right here and separate this into 2 integrals. It may be easier to do that because this one's pretty easy. When I integrate that, that's just going to be x. Now, this next one's going to be a little more complicated. Okay, what if I change u to be the x squared plus 1? All right, and I want you to notice it's in the denominator. Okay, so du equals 2x dx. Well, I'm just missing my 2. Now, when I do this, I've got to be very careful. I need the 1/2 out here and the du. Okay, I had the x dx. That went away with the du. Now, this x squared plus 1, I want you to notice it's in the denominator. So really, when I change that, it's u to the negative 1. So here we go. This is x plus 1/2. All right, this is going to be ln, absolute value of u, plus c. Now go and replace the u. And really, you could lose the absolute values here because we know anytime we square that, it's going to be positive, and then when we're adding 1, it's going to continue to be positive. All right, but I'm just going to leave my answer like that right there. For right now. Now, if we want to manipulate it a little bit, remember, we can take this and raise it to the 1/2, but remember, when we raise things to the 1/2, that becomes square root. So this could be another option that you could have if it's multiple choice. Okay, we do have to think about that for multiple choice and see if we can go back as far as we can. All right, and one last problem that we want to look at here. All right, tan x. Now the problem here with tan x is if I make u tan x, the problem is the derivative of tan x is secant squared. Okay, and I don't see that secant squared and I can't add it in there. However, if I take my tangent and I change it to sine x over cosine x. I start to look and I'm like, oh, wait a minute. What if I can change this so it's sine x cosine to the negative 1x. Now the thing you want to make u is the thing that's raised to the exponent. So if u is cosine x, then du equals negative sine x. I'm just missing the negative. All right, so here it's going to be negative u to the negative 1 du, because I had the sine x dx, I just didn't have the negative. All right, so this is negative ln absolute value of u plus c. Now go replace the u. And my final answer looks like that. So just remember those tricks, and I probably showed you the tricks too early. Look for just basic integration. If you can do basic integration, great. Sometimes you may have to rewrite the function with long division like we did in number 14, or change like tangent to sine over cosine. Okay, you may need to split up things into two integrals. That may make it easier. And then you may also have to use u substitution.